So this is a presentation about the MaPLe compiler for Parallel MP. Um, MaPLe is a compiler for parallel programming on shared memory multi-core machines. The language that it's used is standard ML, which is SML, and it has extensions for parallelism. It uses the work span model. Essentially, that just means that the work part is just the cost of the best sequential execution, which is the time calculated when you run your sequential version, versus span, which is the time that it would take if you had infinite number of processes. So eventually, the number of processes would not make a difference, and it wouldn't help any better. So that's kind of the model that MaPLe also uses. The syntax for MaPLE's executable is kind of similar to when you run OpenMP. It's you just include the program name, which you just create when you run MaPLE and the name of the file that you're trying to run, and then that would create the executable. So then you can just run with that executable program, and then adding the at MaPLE procs would let you add or specify how many processes you want to run with. So we could start with an example. It's a very simple example. This doesn't really involve any parallelism yet. It's just a basic example to show what MaPLE syntax could look like. Here we have a line of code which basically just prints a string, and the string is essentially the argument that's passed into this function print, and it just writes that argument to the terminal. So val of anything essentially just introduces a new variable. So when we add val of underscore, it just prints the thing, but it doesn't really introduce the new variable for the result. So to compile this, I have the file here. All of these examples are brought from the MaPLE tutorial GitHub, which includes a really good list of examples, and I'm just going to show a few of them. So if I were to run this, I'm just going to go to the directory, and I'm just going to run maple hello.sml, which is the name of the file, and that would create the executable. So the name of the executable is hello, so I can just run that. And it should print the value. I could also name it to another file when I'm trying to save this executable. So I would just need to add the dash output flag if I wanted to do that. So I could just do maple dash output foobar. And that would create another executable, and then I can just run that. And it would give me the same output. So this is running one file. There's another file. Here it's called hello again, same line of code, just a different print statement. I in MaPLE typically it's multiple files running together. So one way that we can do that is using MaPLE Basis, which just extends SML to support programming at large, and this includes explicit file order and dependencies and scoping and renaming. And typically, the SML file, when we just run a single file, we don't need to specify the dependencies because it's implicit. But when we're using the MLB files, we would need to specify what the dependencies are, so everything is known when we're creating these files. And yeah, this line is kind of just what is included in the um, MLB file. It just essentially loads the SML basis library, which includes the definition of the important functions that we would need, which is basically just the print function. Um, so I can run the MLB file, which here is just 3 lines of code. It just gets the basis library and then it gets the 2 SML files. So I can just run it the same way using MPL. And then if I ran that, it prints both of the print statements from both of the files. Um, so when we wanted to parallelize the functions, the main way to do it is by calling the par function from the fork join library. Essentially, it just takes 2 functions, the one to the left and then the one to the right. It's a tuple of 2 functions, and it just computes them separately and parallelly. So this one is computed by one process and then this one is computed by another process, and then it just brings both of them together, and then this would be the output of whatever this process does, and then this would be the output of whatever this process does. Um, so a small example, if you wanted to do the Fibonacci of a sequence, we could do that both sequentially and using parallelism. Um, so this is the sequential version. It just takes a value n. If it's 0 or 1, it just returns those values. If not, then it just recursively calls the function on n minus 1 and n minus 2, and then it just adds those 2 values. So if I were to run this, I can just do the same thing, run MPL on the sequential function, and I'm just going to do that using the main MLB file, since it includes all of the dependencies and everything that I would need to run this. And then I'm just going to use time to calculate how long it takes to do this, perform this. So yeah, as you can see, it took about 0.3 seconds to run this. I can run this also parallelly using the par function. So here is an example of the parallel version. Does the same thing if n is 0 or 1, except now if I want to call it recursively, I'm just going to pass in the n minus 1 function into the first part of the dot par function, and then the second part, n minus 2, is going to be passed in to the second argument of par, and then whatever those 2 values return, which is this one would be a and then this one would be b, I would just add those 2 at the end. So we can try to run this. So yeah, it ran, but somehow this is more like it's taking more time than it should for like compared to a sequential version, which is not how it should be. It should be faster. Um, And the reason for this is because fork join.par has a significant cost in the beginning. So if your value of n is not big enough, it's the overhead is probably like too big, and it's probably taking too long compared to if you just did it sequentially. So one way that we can probably fix that is if our granularity value, which is the value of n, is too small, we can just run that sequentially instead of running it using the par function. And the way that we can calculate what this value of n should be, I mean, that's kind of just like test and run. We kind of just experimented. There's no real like way of calculating it. I feel like it's just you just kind of test and run. If n is 20, and if using the sequential is faster, then you kind of just use that compared to if it was like 30 or 40 and so on. So there is another version which is called fastpar here, which basically adds the granularity check, or the control, and it kind of just checks if n is less than 20, that's the limit, and that's where we would run sequential until, and then we run it using par. So if I ran this instead, it's much faster, and it is about the same time as the sequential, and that's because it's not using as many processes as it could use. So if I added more processes, yeah, it's much faster here. I could also try to, yeah, it's 0.1 compared to 0.99. So yeah, somewhat of a linear, like it's not completely linear, but it's still much better than it was. Um, so yeah, that's a Fibonacci. Um, the next example is basically using trees. In MaPLe, trees only have leaves with real values, um, and the tree is essentially just intended to be used as parallel lists instead of like all of the nodes, including the value. So here we have the data type definition, which is a tree can either be empty, a leaf with the value in it, or a node where the first value is the size of the tree or the node, and then it's two left and right subtrees. Um, so one way I will be demonstrating the parallelism here is by using tree reduce, which essentially just takes a function as an argument and computes the sum with the respect to the function of the leaves of the tree. And to test this, we would be using balanced and unbalanced trees. Here, the unbalanced tree is going to be a tree that only creates nodes from the right side of the tree, of the root. So it's all the way down to the right of the tree is where we are making all the nodes, which is height n, compared to a balanced tree, which would be of height approximately log of n. Um, So here is the code for a tree. Essentially, this is the sequential version of using a tree. Um, pretty simple. We just check if the current value of t is empty, leaf, or node. And if it's empty or leaf, we just return the value. If it's the node itself, then we're just recursively calling on the left and the right subtrees, and whatever value we get out of that, we're just calling the function on that. So the function is expecting the values from the left and right, and then it just does something to these values, and then it just returns the complete output, the final output. Um, the parallel version of that is kind of the same, pretty much the same. It just adds a granularity check, which is checking if the size is less than a certain number. We just run it sequentially using this, because using fork join.par is probably not worth it. If it is big enough, then we call on par, and we do the same thing. We call um, the par on the left and the right subtrees, and then whatever result it gets, which is result left and result right, we just call f on that, and that should do it. Um, so we can run this on the balanced and the unbalanced trees. So let's test the balanced first. So yeah, as you can see, the sequential version is about taking about the same time as the parallel version, um, and that's okay. It's at least it's because it's kind of the same amount of processes. So if we were to add more processes to this, um, let's say four, it's much faster for parallel. About um, three times, I would say. A little less than three times, but still better. And then let's test the unbalanced one. Yeah, and here, if you can see it, the parallel version is much slower compared to even the sequential version, which again goes back to um, why it's slower, and it's because um, of the granularity control. We have approximately n divided by the number of grain internal nodes that have a size that is greater than the grain size. But in an unbalanced tree, that number is much bigger, and it's n minus grain internal nodes. And so the cost of par is not effectively amortized, because essentially it's not like splitting up the values of the nodes effectively, because everything is on the right side of the tree. So to ensure balance, we can use structures such as AVL trees or red-black trees or weight balance trees and etc. Or we could use the join function, which is another function that was created, which just stitches two balanced trees together. And this would ensure that we can always make sure that it's balanced whenever we're adding new values to the tree. The future of MPL is essentially just closing the performance gap, which is identifying and addressing other sources of overhead, which contribute to performance gap between high level and low level languages, um, and then managing concurrency bugs, which fix databases and synchronize concurrent accesses to shared memory locations. And this can be prevented using atomic operations, but they do incur additional overhead at runtime. And the solution will be to use a combination of static, which is at compile time, and dynamic, which is at runtime techniques, and then also programming heterogeneous hardware, which includes new programming and scheduling techniques to automatically map computations onto heterogeneous CPU and GPU hardware. Um, and yeah, to reiterate, I used the Docker file. I basically ran the all of this code in Docker to run the MaPLe. Mm, but yeah, thank you for for listening.